Hello, this is a video in which we use calculus to define the natural logarithm function. Now, I'm using James Stewart's 6th edition of calculus, which is very interesting because he goes through this same subject twice. First, he does it from a more intuitive pre-calculus approach, which is probably the approach that your calculus teacher will use if you're, for example, in an engineering or just general calculus approach. However, then he does a Wayne's World. Let's give a different ending. It's not a different ending, but it's a different approach. The asterisk sections. He does the same thing again, but he does it from what he calls a more rigorous perspective. And I suspect if you're in a calculus class for math majors, this might be the way that they approach it. But enough of this talk. Let's get to the natural logarithm function. So let's define a natural logarithm from a calculus perspective. The natural logarithm is, drum roll please, the natural logarithm of x is the integral from 1 to x of 1 over t dt. X needs to be greater than 0. Okay, because the natural logarithm has no negative results, as it were. Okay, so there you have it. Now, you can conceptualize, and you can go to the book if you want to see a graph of this. We can conceptualize the natural logarithm as basically the area under a hyperbola, 1 over t. So if 1 over t is a hyperbola, then the natural logarithm is the area under that hyperbola from 1 to x. So this is a way of, what is an integral? An integral is the area under the curve, right? And so we can conceptualize the natural logarithm as the area under the curve from 1 to x of the hyperbolic function 1 over t. Okay, that's a way to conceptualize it. So here we have a nice little mathematical definition of a natural logarithm. So by the fundamental theorem of calculus, we can say that the derivative of the natural logarithm is 1 over x. It's going backwards. If the natural logarithm is going from 1 over x to the natural logarithm, then the derivative goes from the natural logarithm to 1 over x. And so you can just, these are things to memorize, that the derivative, this is in practice, I think this is important to memorize, that the derivative of the natural logarithm is 1 over x. Okay, that's probably the most important thing to get out of this video, I think, is the derivative of the natural logarithm. Okay, so what are the laws of logarithms? Well, you may have come across logarithms already in your mathematical pilgrimage, in the past. The laws of logarithms are very nice and easy and simple. And when we do our video on logarithmic differentiation, this is going to be very helpful. So the natural logarithm of something times something is the natural logarithm of the first plus the natural logarithm of the second. This is going to be very helpful when we're trying to differentiate really complex things that have multiplied things and divided things and powered things. Okay, so keep this in mind. Second, this also works for logs in general. The natural logarithm of x over y is the natural logarithm of x minus the natural logarithm of y. And then finally, the natural logarithm of x raised to a power, that power pops right out, is the same as r times the natural logarithm of x. These are going to be very, very helpful when we get to logarithmic differentiation. Okay, so laws of logarithms. We're getting close to the end. This is a quick video, as these videos go. So limit rules. Okay, so the limit as x approaches infinity of the natural log of x is infinity. So I'm going to try to do this. I have to do a mirror image, so I hope I get this right. So the way that the natural logarithm graphs is it has an asymptote at x equals 0, but then it comes up and then goes like this above the x-axis, and so it goes to infinity. As it gets bigger and bigger, it goes to infinity. Okay, so the limit as x approaches infinity of the natural log of x is infinity. But however, when you approach 0, when you go the other way, when you approach 0 from the positive side, there's an asymptote at x equals 0, and so it goes down to negative infinity as you approach 0 from the positive side. Boy, I'm sorry, it's not hard. Okay, finally, the number e. So we can define the number e as the number such that the natural logarithm of this number is 1. E is a very important constant. It's baked into nature. God, at the creation of the world, God said, let there be E. It's built into things. And especially when we get to population growth and that sort of thing, we're going to use E. It turns out to be an irrational number because it just won't stop. 2.718281828 and on to infinity with various other numbers. It's not a repeating decimal. It happens to do 1828. I don't know what happened in 1828. There must have been a disaster or something. But the numbers go on, but they don't repeat. They're blah, blah, blah. Okay, so that's what E is. But if this is true, that E is the number such that the natural logarithm E is 1, then basically we can conceptualize it this way, that the natural log of E is the integral from 1 to E of 1 over t to t such that it equals 1. So remember our area interpretation of the natural logarithm, that basically the area under 1 over x from 1 to E is 1. That's what the area is under the curve at E. From 1 to E under that 1 over x hyperbola, that area equals 1. Okay, well, we're done. This is a quick video defining the natural logarithm from a calculus perspective.